Okay. I'm not going to write out the conversions. Everybody needs to know those by now. Okay. And the way you know them is by doing 50 problems. Unfortunately, if I put 50 problems in open math, nobody would be able to do them all. Okay. And the problem there is partly with open math, because I'm not totally enthusiastic about the learning process in open math. It's a good aid. I'm working on the idea of more drill and practice, because after you learn to do it, you can do it fast. And once you've done it fast a few times, it sticks with you. Okay, well, anyhow, as I said, I'm not going to all of a sudden change the approach of this course with the future courses. I want to have some discourse with the rest of my math faculty and see what they think. It's not my math faculty. I'm not even lead teacher this year. Okay, we rotate that on 2 years. If I'm still alive in 3 years, maybe I get to do it again. Okay, so anyhow, assuming nobody else wants to. And I certainly hope that isn't good because we're a generation earlier than I am. There you much kids. Okay, young fellows. Okay, so we got 2 to the x, 2 to the 3x minus 5 equals 4. That translates to log to the base 2 of 4 equals 3x minus 5. Okay. Well, log to the base 2 of 4 is 2, and that ought to be totally obvious to you if you know the graph of the basic log function. Okay? If you invert the 2 to the x values, and you get the log values, and you see log of 4 is 2 because 2 to the 2 is 4. Okay? Now, another way to do this, and this is kind of important to understand, you should know just by inspection that this is 2 because 4 is 2 to the second. We have log to the base 2 of 2 power. Circled in the wrong color. Thought I was doing okay today, but that's not a good sign. Let's fix it. Okay. I'd have anticipated doing this step. Okay. Log to the base 2 of 2, and that is the exponent. Okay. Some might ponder why that's so, but this gives you 2 because 2 is in the exponent when you have the base equal. But when you have the base here, this is the base. When the base is here, your exponent is your base 2 log. And you really are best off if you understand that. So I'm not going to do that. Okay, so you get this. And then everybody knows how to solve the equation. We have 5 on both sides. We get x equals 7/3. Okay. Makes sense? And then, of course, we could check it. If x equals 7/3, then 3x equals 7. 7 minus 5 is 2. And the base 2 log of 4 is 2. Okay, that's 4. Okay. This one. We translate that, it tells us that 5x plus 4 is 7 squared. So that 5x plus 4 is 49. So that x is 9. Subtract 4 from both sides, you get 45. 5 goes into 45 9 times. Now, the whole idea is, in each case, we've changed the form of the equation, changed from exponential to logarithmic or logarithmic to exponential notation. And we got an equation that's very easy to solve. Now, the next two equations aren't that easy to solve. But I thought I'd reiterate properties of quadratics because that's important. Okay, so we have E. To the x squared plus 5x plus 3 equals 30. This would be written as log base E of 30 equals x squared plus 5x plus 3. A majority of the class wanted to do e to the 30th power. Okay, so be sure that you are clear on the inverse function relationship that allows you to change from exponential to logarithmic notation. Now, why do we change from exponential to logarithmic notation? It's because your x is up here in an exponent. You can't get to it otherwise. Okay, you get to it by changing the notation, and now you have it down here where you can do something with it. Okay, can't do anything with it when it's up here. Okay, then we have usually something up. I don't hear like this much. You know, when I'm walking around, I know how far the wall is and I don't walk into it. But apparently, I can't transfer that to the edge of the board. If I walked around like I write on the board, the walls wouldn't have a chance. Okay, well, anyhow, here we go. Okay, this is I almost walked into that wall too, but I squeezed it in there. Okay, I've got equals 0 on the other side. That's all. And then why did I do that? I recognize this as a quadratic equation. Now that log base e of 30 makes it look a little weird, but log base e of 30 is just another number. At this stage, you could punch that into your calculator, but I'm going to rewrite it so you know what to punch in. And see, if I write it as ln instead of log base e, I've got room to write it equals 0. Okay, well, point is, that's what the natural log is. It's log base e. Well, the next thing you have to do is, there are two ways you can solve this. You can just go directly into the quadratic formula. I'm going to write that out in a minute, but first I'm just going to use an approximation. Natural log of 30, which is around 2.4, I think. 3.2 to 3.4. Okay, I think. So let's we'll pretend that that's a decent estimate. And that's, we don't guarantee that, might be 3.3. Did you get it? 3 point what? Don't say it. Don't say it. Hold up some fingers, just for this one. 4, I was right. I was wrong when I said it might be 3.3. It doesn't round off to 5, does it? It can't possibly. It's concave up this. Okay, so we get x equals -5 plus or minus the square root of 25 minus 1.6 over 2. And I'm not going to quote the quadratic formula. That's something we've been over. You just have to know the quadratic formula and recognize what I've done. You forget your b squared is 5 squared, that's 25. Your 4ac is actually it's minus 4ac, so minus 4ac is plus 1.6. Okay. And that's approximately, oh man, I don't approximate that. I'm going to say that's approximately 5.1. I'm going to say it's about 5 points. It's reasonably close to 5 points. Okay, so that's either 0.1 actually that's equal to this. I mean, this is equal to this. It's not equal to the correct solution. This is still an approximation. Anyhow, or 5.1. Yeah. Okay. Now, I might have made an error. I did some estimates there. So you punch these into your calculator. Alternatively, you have this expression, which tells you then that x is -5. And actually, that should be -5. I think maybe I'll let myself enough room, but let's square root of 25 minus 4 times 3 minus the natural log of 30. Over 2. Because C now is 3 minus the natural log of 30. It approximates 0.4, and that's clearly C, right? Answer ax squared plus bx plus c, c then -0.4. Okay. And that's not a bad approximation. If we want it more accurate, we keep it exact. This is your exact solution. Assuming I've done everything else right. Okay, 25 minus 12 is 13. And we get 4 natural log of 30. And that's one circle around this to indicate that's my C value. Okay, well, actually, I'm going to be do one more step in the exact expression. Okay, it's equal to this. And it's approximately equal to your approximations. By calculator or computer, whatever. Okay. So the reason I show this is sometimes you're asked for an exact solution. Not so much in this class, but in pre-calculus, okay? So you need to see that it could be written out in exact form. This is still exact. But the square root, since it's not the square root of a perfect square of a fraction or a real number, or an integer, is not going to be something you can write out exactly in decimal form. It's got to be rounded off at some point. Okay, probably did something ignorant, so we've got a question. Okay, so there's, quite a bit of content in my solution. Should be giving myself more room here. So make sure we understand where this column is separated from this column. If you do this, you're going to get something reasonably close to negative 0.1 and 0.1 and negative 0.1. Okay, the last one, and I better I've got enough order all the way over here, so like move over a little bit. Natural log of x squared plus 2x plus 4 equals 5. And this means log base e of x squared plus 2x plus 4 equals 5. Which means that x squared plus 2x plus 4 equals e to the 5th. Again, you can't do anything with this expression, and you certainly can't distribute the natural log through an addition. There's no multiplication distributes over addition. Nothing else does. In function notation, natural logs and exponentials don't. Okay. There's always a temptation to do that. Okay, well, e to the 5th is a little over 100. So I'm thinking, wait a minute. Two squared, yeah. I'm going to guess that it's 110, but that's not guaranteed to be very close at all. Okay. Over here, it's a bit more, so this equals 0. So x is approximately this. Make sure we know when we're calculating and when we aren't, because that can be important. Okay. Well, this gives us a simple quadratic equation. And comes out 428. And the square root of that is 20.6 or 20.7. I think it's 20.6 something rounds to 20.7, but as usual, it can be way out in left field with the approximations. Check it out yourself. But solution's simple enough. Just know when you're approximating, and that's going to be using the -2, we get 22.7. That'd be about 11.4. That'd be 4 18.79 approximating to one decimal place. Any more would be overreach. Okay. So I think that's probably an accurate solution within plus or minus 0.1. What I'm saying now is, in each case, you can translate this because in each case, the thing you're solving for is in the X term. Okay. And the solution techniques are solution techniques we understand pretty well. Now, what do you understand totally what I did here? The exact solution. Not that important for this course, but you really ought to think about it. You know, see that you could do this. Now these equations, you know, not every equation can be solved. Okay. Are equations you can't solve exactly. You can solve these exactly in the sense that you can write out the exact solution. And I could have written out the exact solution here, but I'd have to use e to the fifth. I'd have 4 minus e to the fifth instead of 106. Okay. And that would have to go into the quadratic formula, just like the 3 minus the natural log of 30 would have to go in here to express an exact solution. You should be aware that sometimes you have to be able to do that. Okay. Now there are equations you can't solve exactly. How about x times 2 to the 3x minus 5. Well, you could divide both sides by x, but that'd take you from the frying pan into the fire. You'd have x's on both sides. And when you convert to natural log, you have an x inside your natural log, and you're stuck. You're in an endless loop of convert this way, convert that way, convert this way, convert that way. The x will always end up inside of something where you can't operate on it. Okay, at least this actually. So this is just for instance. It doesn't take much to make the equation unsolvable. If it's unsolvable, you can still graph it approximately. You can still solve it approximately by graphing it. Okay. Now there are more sophisticated graphing techniques that I really think we ought to be teaching in the course. How would you graph x times 2 to the x minus 5 equals 4? 3x minus 5 equals 4. You can do it by graphing 2 to the x minus 5, graphing y equals x, and multiplying the y values of the two graphs. Or you can take a calculator and use the graphing utility to graph it. Okay, you would get a graph that looks something like this. You get positive y's over on this side. The graph would be an x times 2 to the x type rail, which would have a relative. I don't know. I have a little trouble visualizing it, but it might look something like this. Kind of becomes exponential, and even exponential with a little bit of attitude. But you do that, So what you do then is you put x equals 4 here. Project over and down. And here's your solution. Just like we've done with graph many times early in the semester, early in the course. With the basic functions, okay? So if we could get a graph of this, maybe it looks something like this, maybe not. Still think you have to go back from there, but have to do the calculus. Kind of did it in my head, but I don't trust it. Okay, and thought about it previously. The idea is you graph this and you find out where it's equal or y is equal to 4. And landing x is your solution. Okay, that's an important thing to be able to do because many times in reality you have a function that's even more difficult to graph than this. And that's kind of tricky to graph, but boy, the functions can get really complicated, really weird looking graphs. You have to understand how to use the graph to estimate a solution. Okay. When I say you have to understand the graph, get a solution, you have to be able to understand what to do with the graph to get the solution. That's not even strictly true. You can always go to Wolfram Alpha and get a solution without understanding a bit of anything. Even knowing when you need the solution, though, isn't necessary. So I think you're much better off understanding how the graph relates to the solution so you can kind of visualize things. Okay. Comes down to the question of you understand the mathematics, you just punch it into the system to get the right answer. Sometimes you want to do both. Okay, we're going to switch gears here. We're going to start with a familiar problem. Well, yeah, I was going to put in concepts, but I'm not going. I think that has an integer solution, but whether it does or not. Okay. All right, now, I'm going to call this equation 1. We call this equation 2. We want to find a value, find values of x and y that solve the equation. Now, we've already talked, I think, in this course, and if not, well, I'm going to change this equation a little bit and make it 5x minus 12y. Just like your graph is like most we didn't need. And that's going to equal -19. Well, I can find my x and y intercepts very easily. The x-intercept occurs when y is 0, in which case 3x equals 17, so x is 17/3. So now I have a point 17/3 0 on the graph. If x is 0, y equals 2 3/4. Okay, 17, 2, 3 sevenths, 17/7. So I have the point 0, 17/7. And now I have a graph that more or less goes through those points. I can do the same here. If y equals 0, x is negative 3.8, okay? Negative 19/8. That might be here. I'm not bothering with a good scale, so I can get a really inaccurate solution. And that should be x. It's negative 19/8, which would be on this scale, maybe about here. And then if x is 0, y is 19/12, which is a little more than 1.5. So this point is going to be 0, 19/12. And my line is going to be here. Now I can convert those to decimals. I could put it on a scale. We done this in here? Okay, well, you know how to graph straight lines, presumably. We have done that. So just graphing this straight line and this straight line using the intercepts. I see that the straight lines cross at a point here in the first quadrant. And if I've got a scale and graph this carefully, I can do a pretty good job of estimating the coordinates of that point. Now, if this is 17/3, that's almost 6. So 3 would be about here. And 1.5 would be about halfway. I'm going to say that's maybe 1.2. And 19/8 is almost 2.5. No, 17/7 is almost 2.5. And if that's 2.5, it's 1.25. I'm going to say maybe that's 1.8. Now I'm just kind of converting these fractions in my head. Might have well made a mistake. When you graph these things, you're not going to get a completely accurate result unless the problem is contrived to give you what you expect. Now, I did contrive this problem, but I wasn't thinking about my contrived values when I estimated these, but they turn out to be fairly close. Okay. So, how do these values do? So we have an estimated solution. And we want to check that solution. Check the solution. You got 3x plus 7y equals 17. Equation 1 says that 3 times (1.2) plus 7 times 1.8 should equal 17. I'll put a question mark over that equal sign because we're asking, does this equal this? We don't expect that it really will, because in the first place, I did this graph without drawing a scale. My points aren't that precisely located. And even if they were, you wouldn't expect a hand-drawn graph to give you a really accurate solution. Well, if we do this, 3 times 1.2 is 3.6. Okay. 7 times 1.8 is 11.8, I think. Okay. So 3.6 and 11.8 is 15.4. And this is close. Means I expect my actual solution to be not too far from 1.2, 1.8. That is, provided that it works here too. So the second equation would be 5 times 1.2 minus 12 times 1.8 equals negative 19. Well, 5 times 1.2 is 6, and 12 times 1.8, and well, 12 times 20 is 240. You subtract 24, and you get 226. That'd be 6 minus 22.6, be negative 16.6. That's also reasonably close. It's not that far off. You can check my arithmetic, but I think we're going to be about as close as what this indicates. The answer to both questions is we're not exact, but we're close. Now, the question is, how do we find the exact solution? Well, there are 2 ways to find the exact solution. And you should be familiar with this algebra 2 and stuff. You could solve this equation for x. You would get what? You get 17 minus 7y all divided by 3. You just subtract 7y on both sides and divide by 3, and then plug it in for x here. You get 5 times the quantity 17 minus 3x over 7. And you multiply through by 7 and do the solution, and you get a value for y, because I think I said 17 minus 7x is 17 minus 7y over 3. If you solve this for x, you get an expression in y. If you plug it in here, you're going to have an expression for y, and you're not going to have any x's in this equation. You're just going to have y's. Okay. Then just use your techniques for solving linear equations, and you get a solution. That should be familiar somewhere in the vestige of your consciousness. You should have done that at some point. Okay. During COVID years, I don't know. And if you haven't, take my word for it, it's not hard, but we're not going to do that in this course, because that's something you should already know. And if you ever need it, you can usually pick it up. What we're going to concentrate on in this course is how to solve these equations by elimination. And we might come back and talk about substitution. Open Math might talk about substitution a little bit. It's not that it's unimportant, it's that something that is so prerequisite that we shouldn't even have to talk about it. Okay? And it's so prerequisite that it's not very hard. So if you ever really need it, you can find it. Okay. So by elimination, okay, again, we have equation 1 is 3x plus 7y equals 17. Equation 2 is 5x minus 12y equals negative 19. There's our system. if I multiply this first equation by -5, I get -15x minus 35y equals -85. Now, why in the world would I want to do that? These numbers are bigger than these numbers. Well, the reason I want to do that is because I'm also going to do this. I'm going to multiply this equation by 3, and I'm going to get 15x minus 36y equals -57. And multiply by 3, that's right. Okay. Now, let's just talk for a minute because I've been talking for way too long. Okay, so as I said, okay, the one observation I got is they're both linear. Okay, well, that's a good observation. As I said, that's what you really want to recognize. Because in the first place, what we're doing here only works if you have linear equations. Okay. If you recognize when you have a linear equation, you know you're going to be able to solve it. It's very easy to solve. It's a 17th degree polynomial. The way I said it is, the response is, come here, Wolfram. Okay. You probably don't even try to figure out its graph. You just know it's going to be really steep on both sides. Go to infinity, one side negative infinity, and the other just well, the coefficient is positive or negative, and probably has some zeros in between, has to have zeros in between. You know all that. That's probably about all you'd be able to figure out. All I'd expect you'd be able to figure out. Okay. Well, why do we have linear equations here? Well, we notice that these are linear. And if we multiply both a linear equation by same, multiply both sides by the same number, which is what I mean by like multiplying -5 by the whole equation, multiplied by both sides. Then multiplying this equation by 5, this is linear, this is going to have to be linear. You're not going to get any x squareds or square roots of y by multiplying by a number, right? And this equation is totally equivalent to this one. Every solution to this equation is a solution to this one. The graph of this equation is identical to the graph of this one. If I figure out the intercepts, I get exactly the same intercepts that I got from the original equation in every sense. This equation is the same as this one, and this equation is the same as this one, assuming I did the multiplication right. Okay. I have to double check, so I could be wrong. And if I did get the multiplication right, they are equivalent. So the solutions I get from these won't work up here. Okay. Now, what else though? If I look at the coefficients of x and the coefficients of y and the numbers on the right-hand side, there's one thing that should be pretty clear. Okay, so we see that we have 15s in front of the x. And what is it about the 15s? Well, they're opposite, okay? And that's going to be really handy because what I'm going to do is I'm going to now add the first equation to the second. More implicitly, this is now my first equation and this is my second. I don't go all the way back to this one. Okay. So what do I get if I add this side to this side? And what do I get if I add this side to this side? Okay. So the first thing you see, if you add these sides, well, first thing you're probably going to do is add the -15x to the 15x, and it's going to give you 0. It's 0x, but 0x is 0. 0 times x is 0, right? So we get a 0 here. And then we do the rest of the arithmetic. We get -71y, and that equals -142. Yeah, I think so. Okay. Oh man, I wasn't even looking at what I was looking for, but it looks like when I divide by -71, I'm going to get y equals 2. I'm really excited because that's what I was hoping I would get. That's what I intended to get. But you know, my brain doesn't always get it right. Okay. And I didn't care. I mean, if we didn't get an exact integer, we'd still get a number that we can compare with the 1.2 and the 1.8. Okay. So, yeah, the 1.8 made me kind of happy because I knew why I was supposed to be 2. Well, this tells us applies to, not going to solve that just yet. Well, actually, I am. Okay. And 2 times 70 is 140. 2 times 1 is 1. We're dividing both by negative, so we're going to get. Okay. You should be able to see that. But if not, most of the time you're going to end up having to use a calculator anyway. Now, this was a contrived problem. It's not the kind of problem that usually pops up in the real world. It's usually not going to get such a nice result. Okay, it's not that I was trying to be nice to you. You know, I'd never do that. Just wanted to have something we could really see and compare. So 2 compares pretty well with 1.8, right? Now, how are we going to find the value of X? Any suggestions? Okay, well, that's pretty good. And just realized we're out of time, so we're almost done. Okay, so I suggest, well, you just plug Y in the other equation, okay? And we want to go back to the original equations. We don't want to plug into one of the equations we got in the process. So we plug Y equals 2. It's easiest to draw the arrow to the first equation. And out of that, we get the equation 3x plus 7 times 2 equals 17, which is 3x plus 14 equals 17. And finish out the solution. You subtract 14, you get 3 on this side, 3x equals 3x equals 1. Okay. That's the exact solution. Would be 1, 2. And that's consistent with this solution, not exactly equal to it, but it's not far off. Okay. Okay, it's consistent with the 1.2, 1.8. That we got. Okay. So that's the process. Open Math's going to ask you to do several of these, and they're not difficult. It's going to give you several examples. We'll start off with really easy ones, and it'll get into ones that aren't too much harder than this. Okay. Probably no harder.